see a portion of the Large Magellanic Clouds, and I don't have to ask you which the star is that underwent the explosion. It's quite clear. And now the next slide is a picture taken with Hubble Space Telescope. It's an extremely famous picture. So this is the location where the star was. You still see light coming from there. And much to everyone's surprise, do we see a bright ring here? And which is even more of a surprise, are these two rings. This has nothing to do with the supernova. This is just a star which happens to be in the same direction, and this also is a star in that same direction. But if now you look with a telescope like the Hubble, then you see this amazing picture whereby matter from the explosion is streaming out in all directions. And if you push me very hard, maybe at the end of my talk, I can talk to you about why there is this crazy ring. We understand this ring, but this is more difficult to understand. So it's an object that is still under study. And in fact, when you see pictures with a few years intervals, you can actually see changes. Something is changing. And so now comes the question, the $64 question is it now true what Zwicky and Bade suggested, that when there is such a supernova explosion, is it true that a neutron star is formed? That's what they suggested. So you could ask the question now, is there at the center of 1987A, is there a neutron star? And you better believe it, that hundreds of astronomers have tried to find a neutron star at the center of 1987A. There even has been a publication in which it was claimed that it was seen, but that was later withdrawn. And it's fair to say that no, it hasn't been seen yet, but maybe it may take another 20, 30, 50, or maybe 100 years before the neutron star will clearly be visible. Because there may still be so much debris around the neutron star that we don't get to see through the debris. That is still quite possible. But we still believe that Zwicky and Bade were correct. And the way we know that is that as soon as the idea of pulsars was published, people asked the question, if we look at supernovae that went off a long time ago, and we look in the same direction, can we perhaps find neutron stars? And you can see the remnants of a supernova for quite some time, for many hundreds of years, for many thousands of years even. We call them then a supernova remnant. And there is a very famous supernova remnant. It's called the Crab Nebula. You will see a picture of it and you may understand why we call it the Crab Nebula. And that supernova went off on the 4th of July, believe it or not, talking about fireworks. On the 4th of July in the year 1054, on American Independence Day. And this supernova was observed, clearly naked eye, in 1054, there were no telescopes yet, was observed naked eye by Chinese astronomers, and they called it a guest star. And these Chinese astronomers were well paid by the emperor. It was their task to advise the emperor. And they interpreted the sky, and they believed that the sky was telling them stories that they would have to tell, they would have to interpret them and tell the emperor. For instance, the appearance of comets could mean that there was going to be a shortage of food. So they would tell the emperor that they better do something about that. And so the appearance of guest stars, which we now call a supernova, was also something that they were very well aware of. I do not know the exact meaning. Maybe it meant that a disease would break out. Whatever it is, the emperor was informed about it. And so they made very accurate records of these guest stars. And so the one in 1054 was very well recorded by the Chinese astronomers. It was visible during the day for many weeks, that you could see it with naked eye during the day when the sun was up. It was that bright, because it's not that far away. It's in fact so close you can almost touch it. It is only 5,000 light years away from us. That's nothing. 5,000 light years, that's nothing. So it is so close that you could see it during the day, and it was for months and for years it was the brightest star in the sky at night. And yet, there isn't a single record found in Europe. And that is still so puzzling. They couldn't have missed it. Now, I agree that in Holland, where it always rains, yeah, they might have missed it. But in Italy and in Spain, that's a different story. And there isn't a single record for a star that was visible during the day, that was the brightest star in the sky for years on end. Not a single record. Still a mystery. Maybe it was seen by the Navajo Indians in this country, and whatever little evidence there is for that, I will show you very shortly. There's a cave drawing that could be interpreted as the supernova in 1054. To make a long story short, in the 19th century, when telescopes came along, the remnant of this explosion was rediscovered in the constellation Taurus, and it has a little bit of a crab-like structure, and so it's called the Crab Nebula. And so, as soon as Anthony Hewish and Jocelyn Bell published their paper on pulsars, Professor Stalin at MIT aimed his radio telescope at the Crab Nebula and discovered a pulsar. And a few weeks later, the period of the pulsar, how fast it rotates, was discovered by a big telescope in South America. And it was found that the neutron star rotates 30 times per second. So it rotates around in about 30 milliseconds. So that means if you are at the equator of this neutron star, then you go very fast, about 1% or so of the speed of light. Let's take a look at the Crab Nebula. This is the Crab Nebula. So this is at a distance of about 6,000 light years from us. And this is the star, which is the neutron star. This is the one that exploded on the 4th of July, 1054. And this matter that you see here is streaming out, very high speed. You cannot see this with the naked eye, it is too faint. But if you would look at the moon at the same time, the moon would be about this big. So to give you an idea of relative size, of course the moon is very close. And this is at a distance of 6,000 light years. The light to go from here to here would take 6 years. So the distance here is 6 light years. It's a huge object. But to give you an idea of how small it would look in the sky, it's about only 1/6 of the size of the moon. Next slide is that cave drawing from the Navajos. And it is conceivable that this is the supernova. The moon comes very close to the Crab Nebula, and so it is possible that they made this drawing, the moon in connection with the supernova. But other people argue that it is more likely that this is Venus. The moon often comes very close to Venus. Venus is also very bright, so we will never know. But there is the possibility that this was observed also in the United States. The next slide is a wonderful scientific endeavor, which tells us that this star is that neutron star. And what you're looking at here is a picture of the inner portion of the Crab Nebula. You remember you saw the two stars, and I said the one at the lowest one of the two is the neutron star. This star rotates 30 times per second around. And not only does it sweep a radio beam around us, like the other pulsars do, but it also sweeps around a light beam. Very few pulsars do that, but this one does it. A light beam, really like a lighthouse. So this star blinks at you 30 times a second. Well, actually, it blinks twice per rotation, because it has two magnetic poles, so it's really 60 times per second. That's a detail. And so this picture is taken in a clever way with a rotating disk in front of the telescope, which only exposes the photographic plate when the star is bright. And then this picture has the same exposure time, but it only exposes the photographic plate when the star is faint, when it is not bright. And you see that this star and this star have the same brightness as you expect, because this star is not blinking at you, and this star has the same brightness, but this star is gone, finished. And that's because here it was bright, you were in the light beam, and here you were outside the light beam. And so conclusive, 100% certain that that is the neutron star. All right, so I've convinced you that white dwarfs exist. I've convinced you that neutron stars exist. And now I've got to convince you that black holes exist. That's the last thing. That's the weirdest of all. Black holes were discovered in an indirect way through a very young field in astronomy called Xray Astronomy, and Professor Razio mentioned Xray Astronomy. It was discovered in 1949 that our sun emits X-rays. Not very much, only a small fraction, 1/1,000,000th of the total energy of the sun, only 1/1,000,000th comes out in the form of X-rays. And these observations have to be made from outside the Earth's atmosphere, because the X-rays are 100% absorbed by the atmosphere, by the air. Nothing gets through, so you have to get out. And it was discovered in 1949 by Herb Friedman, who used the V2 rockets, which were developed under Hitler Germany by a guy with the name of Werner von Braun. He developed these weapons in Peenemünde, and they were used to bomb London. Hundreds of these V2 rockets were launched and indeed hit London. And this same Werner von Braun became a hero in the United States later, which is something that still puzzles me to date. But in any case, his V2 rockets were used for scientific purpose after the war, and with these rockets, X-rays from the sun were discovered. And then in the early 60s, it was discovered also using instruments that go outside the Earth's atmosphere, rockets, balloons, and later satellites, that there are actually objects that are so bizarre that they produce about 1,000 times more energy in X-rays than in the optical light, whereas the sun, it's only 1/1,000,000th. And here were objects that when you look at them, you see a very faint star, and you see 1,000 times more X-rays than you see light in the optical. It was a real puzzle what these systems were, but it became clear in the 70s that what these are binary systems. There is a star, something like our sun, and then here there's a neutron star. So small that I cannot even draw it, of course. And this is a regular star, burning its nuclear fuel, and this is a dead star, this is the neutron star. And they are so close together that the neutron star sucks off material. Gravity sucks, remember? Pulls. So it sucks off material which goes to the neutron star. And when it falls towards the neutron star, it gets an enormous speed because the neutron star is so small. But it keeps falling, keeps falling, keeps falling. Nothing is there to stop it. And so by the time it reaches the surface of the neutron star, it could easily have a speed of about 1/3 of the speed of light. Something like 70,000 miles per second. An enormous speed. And when that comes to a halt, you get heat, remember. I told you that many times now. Energy of motion comes to a stop, you get heat. And so the neutron star becomes very hot, 10 million degrees, and starts to emit X-rays. The higher the temperature, the more likely it is that the source becomes an X-ray source. To give you some respect for a neutron star, if you take a marshmallow and you throw from a large distance, say a few hundred miles from a neutron star, you throw a marshmallow onto a neutron star, then that marshmallow will crash on the neutron star with about 1/3 the speed of light. And then the energy that will be released in terms of heat is comparable to the atomic bomb that was used on Hiroshima and Nagasaki. That is how much energy is released if a marshmallow hits a neutron star. So that gives you some idea of how much energy can be released when matter from this star, we call this the donor, and this is called the accretor when that matter falls onto the neutron star. And so I want to show you, we have to lower this again. I want to show you a picture of what it might look like, and then also the observational evidence why we believe that they really exist. So this is what it should look like, very roughly. You will have here a regular star, not too different from the sun. And here you would have this neutron star, right in the middle there. You cannot see that neutron star, it's too small. And then the neutron star pulls so hard, gravitational force is so high, that matter will swirl in and ends up right at the center, and then the X-rays come right from here. And so the optical light that you see comes from this star, from the donor, and some from this disk, but the X-rays come only from there. And that explains in a very natural way why you can see 1,000 times more energy in X-rays from this point here than you see the light from the system as a whole. And the evidence you see in the next picture, which is a signal in X-rays. This is time from here to here. This is a time axis. From here to here is about 1¼ second. Gives you an idea for the timing. And an X-ray telescope, which was in a satellite in orbit, discovered pulsations. Don't look at the bold line that was drawn in there, but this is maximum, maximum, maximum. You see pulsations in X-rays. And this is when the matter falls onto the magnetic poles of the neutron star. You get two hot spots on the neutron star, and if the neutron star rotates around, then you see the hot spots, you see the hot spots, you see the hot spots. And so, in a way, somewhat similar to the radio pulsations, do you now see X-ray pulsations. But not only do you see X-ray pulsations, you also see sometimes that the X-ray signal completely disappears, and that happens when the neutron star hides behind the donor. They go around each other, it's a binary system. And when it hides behind the donor absorbs the X-rays. You see that on the next picture, the next slide. So here you see, from here to here is about 1.5 days, 1.7 days. And so you see here the X-ray signal. This is the number of X-rays per second, and this is time. And you see a very bright X-ray signal, and then all of a sudden you see nothing. We call that an eclipse. The neutron star hides behind the donor, and then it comes out of behind the donor, and then it goes into eclipse. So you see here, in front of your own eyes, it's a binary system, and you see the rotation of the neutron star. So everything is just as we expected, and that explains then the high emission in X-rays. So now, what has this to do with black holes? Because we already discussed neutron stars, so there is no sense in going into the details of the neutron stars. Well, when you have a system like this, that you have a binary system, astronomers can measure the mass of these stars. And they do that using an effect that is called Doppler effect. And you may be familiar with Doppler effect of sound. When a train approaches you, that the whistle has a higher pitch than when the train goes away from you. And if you're not familiar with that, I will demonstrate it to you. It's easy to hear. If I move my hand towards you, and I hold a tuning fork in my hand, which produces a nice tone, this is something like 4,000 hertz, very high pitch. Then if I move my hand towards you, you will hear a higher pitch. And when I move my hand away from you, you will hear a lower pitch. That's called Doppler effect. And in fact, if you would record very carefully how high the pitch is when I move my hand to you, and how low the pitch is when I move my hand away from you, you can calculate uniquely what my speed was. If I move my hand towards you 1 meter in 1 second, it's about 1 meter in 1 second, then you will see a frequency shift of about 0.3%. But if I move twice as fast, you would see 0.6%. And if I move 3 times as fast, you would see almost 1%. So I want you to hear this Doppler effect. And I want you to appreciate, as you listen to the change in pitch, that once you record that, you can then derive the speed of this object. I'll first aim for you, and I'll come back to you later. You hear it? Here. Very nice. You're in for it now. You hear it? Pitch high when it comes to you, pitch low when it goes away from you. So now imagine that you have a source that goes around in a circle. I can do that too. This is a sound source that goes around in a circle. This is the pitch. If it comes to you, you hear a higher pitch. When it goes here, you don't hear very much difference. And then when it goes away from you, you hear a lower pitch and a higher and a lower. And so now you hear a very nice modulation, not as sharp, high, low, but more smooth. You ready for this? I'll come closer to you. So this is Doppler shift from a rotating object. Yeah? Okay. Okay, so now you know what Doppler shift is for sound. It so happens that when these two stars go around each other, there is also a Doppler shift of light. There's a color shift of the light. When this star comes to you, it looks a little bluer than when it goes away from you. And if that is studied very accurately, which astronomers can, they can actually determine the velocity of these two objects. And the mass of the stars follows from their velocities. So Doppler effect is used to measure the mass of stars. You can only do that if you have a binary system. And indeed, in the object that I showed you earlier, you find that the neutron star has a sort of mass what you expect.